I'm going to talk about Christoffel Darboux analysis, what I call. It's a very long story. It's a concept which has roots in mid-19th century, and probably all of you met more or less Christoffel and Darboux in connections with orthogonal polynomials. What I want to show you is that this concept has new facets and quite interesting applications. They are part of my joint work with a whole consortium. I'll mention their affiliations in the slides a little later. And what I plan to do is to show a little the history, just tangentially, and then to go into three different aspects of Christoffel Darboux, what I call analysis, namely shape reconstruction in two variables, the analysis of dynamical systems using the ergodic hypothesis, and third, the isolation of outliers in big data. So all they are connected somehow with Christoffel and Darboux. I'll have some slides in the second part of the talk with many numerical experiments, but first I want to show you what I see the origin and what this beautiful idea can lead to. So all started with quadratures, as probably you very well know. And Christoffel in 1858 used what we know now as a Christoffel function for continued fraction expansions and quadratures. And then Darboux a little later, 1878, was using the same idea for series expansions of functions in different, not necessarily polynomials, but having some orthogonality in the background. So what it is all about? In modern terms, let's work with one or several complex variables. I denote by C of Z the ring of polynomials. And if I put a sub D here, means polynomials of a prescribed degree. We encounter in many applications, in many problems, the polynomial ring, and what produces the Christoffel Darboux function is, so this is one, an inner product. Which lives, let's say, on polynomials or more general functions. Once we have this, we can speak, of course, about point evaluations. Linear functional. Let's suppose that we are in the finite dimensional space of polynomials of degree up to D. This can be written, obviously, as the inner product with another polynomial which depends on D. Let me put a sub D here, meaning that we work on degree up to D. This is, if you want, the Riesz lemma in finite dimensions. Very simple representation of a linear functional. The dependence on Z is transmitted to this, and is also polynomial. And what is remarkable is that this K, D, W, and Z is a positive semi-definite what we call kernel, polynomial, analytic in W, anti-analytic in Z. Can work in several variables, can work on varieties, can mod out with ideals. More or less everything goes unchanged. Well, if we have this and we have the inner product, immediately we can speak about the optimal value. So we simply use the Cauchy-Schwarz inequality. And we remark immediately that if we take the maximum of the point evaluation versus the norm for all polynomials of degree up to D, let's say is a non-degenerated norm different than 0. This is achieved, and it will be precisely the norm of this representing polynomial functional, which is nothing else, as you probably very well know, is the value of it on the diagonal. We prefer to work with inverse. And as a definition, KD is called the Christoffel Darboux kernel. And lambda D, which is the minimum of the norm square of P of Z is 1, the degree less than D. It's just the square of the reverse of this fraction. It's called the Christoffel function. And as you probably know, this enters deeply into the theory of orthogonal polynomials, the asymptotics of the leading term, and in general of a family of orthogonal polynomial is encoded into this quantity. And it's quite interesting to see that this is also related very much to spectral analysis of self-adjoint and unitary operators, as I'll mention in a second. And now, with these preparations, I want to show you a few classical applications. Maybe just a remark. We can compute this kernel and the function in many ways, but one classical expansion is in terms of orthogonal polynomials. Suppose it's non-degenerate inner product. These are the orthonormal polynomials of degree exactly k. And, but we can choose any other orthonormal basis for this purpose. So the first application. Uniqueness in the moment problem on the line. Suppose we are prescribed a sequence of real numbers, and we are asking whether there exists a measure which represents them as moments. Classical problem a solution due to Hamburger in terms of the positivity of the Hankel matrix. I'll not go into these details, but we are interested whether the solution is unique or not. And this is hard. Was discovered relatively late. There are studies of Stiltiez and Chebyshev-Markov in the 19th century by Marcel Ries. And the statement is extremely simple. Let's think a little. If we have this positivity of the matrix, we have automatically, we are in the setting I just mentioned. We have an inner product on polynomials. This Sk plus L is the correlation matrix of the monomials. So we can speak about the Christoffel Darboux kernel for every D. We can speak about the Christoffel function. And here is the result, Marcel Ries. (1923). And Nevanlina, different proof, 1924. The problem has a unique solution if and only if the Christoffel function, the limit d tends to infinity of lambda d, of this data is 0 for z not real, for at least one z, and then it is for all. So it's if and only if. The only problem is that this function is very hard to compute, and this is why we have only sufficient criteria due to Karleman and also Marcel Ries and many others, but it's a definitive result, and since then it put the Christoffel function into a very prominent light. If it's not unique, if this limit is not 0, it's even more interesting, because then the closure of polynomials gives rise to a space of entire functions, and this is what we call now the Branch-Rovniak spaces, and it's a whole theory. Some people do approximation and interpolation in this setting. So that's the first setting. Related to this, we can ask, since we are at the moment problem, about the maximal mass. So let's fix a point x naught on the real line. And let's look at the moment problem. The measure mu is behind. And let's interpret a little this Christoffel kernel. So this lambda, first of all, is non-increasing. Why? Because we take the minimum over a larger class of functions, so the limit exists always. And if we look at the definition, we minimize this quantity over all polynomials which at x naught are 1. So this is bigger than, obviously, the mass of the measure at x naught. And this is nothing else than lambda. And in fact, we have equality. This is due to Mark Crane in the 30s. culminating a lot of work, Chebyshev, Markov, and so on moment problems. So this function detects if we are with a moment problem and we prescribe a point, how much mass a solution can charge a respective point. And this is precise, it's exact. I just serve some of these observations, and the last one, before I'll turn to some pictures, is the unit circle. Suppose we take the following variational problem, very similar. We fix non-negative weight, let's say integrable, and we see the mean square variation with respect to this weight on the unit circle. What has to do this with the previous problem? Well, quite a lot, because Z is 1 over Z bar. So I can put a bar here. This will not change the problem. I can divide by this, and in fact, we'll have the minimum of a polynomial, analytic, square, which at the point 0 has the value 1. Yeah, because I put 1 over Z and multiply. Well, that's the Christoffel function of the respective weight at the point 0. So now we are in the unit circle. The measure sits on the boundary, and we evaluate the Christoffel function at 0. Maybe you recognize here, this is a very classical problem. This can be written as the geometric mean of the logarithm of the weight against the normalized measure. And this is Seger, 1914. So the famous Seger limit theorem is nothing else than an evaluation of a Christoffel function on the unit circle. This can be moved to any other point by conformal mapping and leads to density of polynomials in L2 spaces results of Kolmogorov, Crane, and many others. So these are just 3 aspects of Christoffel function in action, a little beyond what you encounter in the theory of orthogonal polynomials. And now more recent results. Spectral analysis, which go hand in hand with what I mentioned. And to give a general statement, let's consider mu a positive Borel measure on the line. And let's decompose this into the Lebesgue decomposition, absolute continuous part, singular continuous, and discrete. What we remarked in point 2 immediately gives, if we work in L2 of this measure, let's suppose that the polynomials exist as elements in L2. That means mu has some decay at infinity. In this situation, we can speak about the Christoffel function at a point, and the interesting part is for a point x0 on the line. And this will detect exactly, the discrete part of the measure. So the limit, you remember this is the limit of the finite kernels, gives you precisely the point masses of the measure. So this takes care, this limiting procedure, of the discrete part. What is more interesting, and these are very recent results culminating almost a century of partial observations, is that if we take the limit of d times lambda d mu of x, d tends to infinity, this will be w of x almost everywhere with respect to the Lebesgue measure. Or more precisely, here we have to divide by the equilibrium measure of an interval or a collection of intervals which contain the support of mu. So, good news. In this function, we have the point masses, and we can isolate the absolute continuous part. This is a result due to Mate, Nevai, and Totic. I have to look, I think 1991. And then the culmination of all similar theorems goes back to Totic in 2000. I'll give you a reference in the very end. So for spectral analysis, you have a, let's say, cyclic self-adjoint operator, bounded or not. You want to find the fine structure, the point masses, the absolute continuous part, the singular continuous part. This tool, which is computable in finite many terms with the orthogonal polynomials or just point evaluations, is extremely useful and important to unveil this decomposition. And now I'll show you a few applications, as I mentioned, of these results. So I'll turn, with your permission, to some applications. Again, I'll surf only the results, but a picture maybe speaks more than precise statement. What I have to mention, and again I'll give references, Barry Simon became very interested, and he wrote quite a few papers about the relevance of this decomposition for spectral analysis on the circle or on the line. I know this is a meeting about multivariate, so we'll go to several variables at a certain moment. So I start this one and put the screen down. There are many things here. I'll go rather fast just to show you a little that this old and tired tool is still of interest. So, first, we have a collection of islands. We call them an archipelago. And we want to reconstruct them from moments. We know the kernel. The normalized Christoffel function here is with a square root. What is important inside, if we have uniform mass, let's say 1 of these islands, this behaves like the distance. So for reconstruction purposes, it's great because you have a distance function inside. Outside will decay very fast to 0, exponentially. And on the boundary, this is very much as this estimate is like 1 over n. So here are some pictures. You see how well this approximates, and just with a few moments, this is up to degree 5 or so, it approximates the square. At the corners, of course, you expect some distance. And so even if you have separate islands, this recognizes, and you see very quickly that in particular there are 2 islands, and you have the boundary quite sharp. 3 islands and so on. And what happens if you have very few moments, I don't know, 3 or so, you get some aberrations, but not much. Second, let's take a break. We turn the page. We have a very nasty dynamical system. And we want to understand, at least to classify these dynamics, using an idea of von Neumann and Koopman. This is called the Koopman operator, but in fact von Neumann had the idea. Namely, if the dynamics is this one, can be very nonlinear, very complicated, you go into a space of functions, we call them observables, and you compose with the dynamics with the functions. So it's the shift on the trajectories, but seen on a function space. This is called the Koopman operator. And if you are in the ergodic situation, you can essentially compute from data, I'll show you pictures in a moment, the moments of this turns to be unitary. And you can do exactly, as I mentioned before, spectral analysis. So the dynamics seen on a function space turns now into unitary operator, ergodic action, and we are interested to, in particular, to see if this elusive singular continuous spectrum exists. And the theorems are here, I just mentioned. And here it is, just a test for a few point masses with number, the degree is 100, which goes very fast with the computers today. You detect very quickly the flat support and the point masses. So the atoms are there. The absolute continuous part also becomes clear with the other limiting procedure, is this one, the dotted line. And if you go to 1,000, it's becoming extremely accurate. Now, what if you add a Cantor set, a singular continuous part? That's more interesting. And you will see some disturbances here, but we are not yet able to determine whether this is singular continuous or not. And for that, we have to do some Cesaro means and the density distribution, the distribution function of this measure, and then it becomes very clear. So these are the Cesaro means, and the FQ means quadratures, and then we take the distribution function, and this will tell precisely that there exists a singular continuous spectrum. That's a toy example. It was just to learn the method. If we go to more complicated and known systems, for instance, this cat map is an algebraic system on the torus, where we know analytically the spectrum, we detect precisely what is going on. The distribution function, the singularity indicator is 0 for this, so it means that there is no singular continuous spectrum. The famous Lorentz system. Here we take different observables, the coordinates x1, x2, x3. No action on the first coordinate, no action on the second, a lot of action here. So this is an indication, a very clear indication that the third coordinate in the Lorentz system is responsible for a singular continuous spectrum. And so on. I'll not go more into these details because I want to show you something else. The cavity flow, this is not known analytically, just big measurements, and here again we have an indication of singular continuous spectrum. You see, there is this discrepancy shows immediately that there is a singular continuous spectrum on the system. So at least this method doesn't give you everything about a dynamical system, but it will tell you, it will distinguish between different dynamical systems by looking at these diagrams. And we have estimates. I'll give you the references in the end. 3, outlier detections. It's very fashionable nowadays to take big data and to try to separate outliers from the cloud. Here are some experiments. These are level sets of the Christoffel function. And they don't do extremely well, as you can see here. We have only 1 point outside. But we can improve. And what is coming into this, this picture, now we are in several variables, is a play of potential theory, the complex variable and the green function of the cloud, and how fast we approximate this point distribution to the measure, to the uniform mass. So there are several players here. And I'll mention quickly how we do these computations. This is very recent work. So the outline is the following. We have a measure, we discretize it with equally distributed points. And the question is how fast the discretized Christoffel kernel converges to the real one. And if we take this perturbation with point masses, we call them outliers, how can we distinguish them? And the good news is that there is a leverage score, which is just the inverse of this weighted Christoffel function. So the inverse of this is between 0 and 1, and this has some statistical meaning and will give you the precise estimate. Again, I don't go into much detail here. The major observation is that we can do perturbation theory of Christoffel functions. So what happens if, let's say, we add 1 point mass to the measure, and this will shift a little the level sets, but not much, and we can control this precisely with essentially linear algebra, with matrix analysis tools. And if the discrepancy between the two measures is not that big, that means the spectrum of this relative moment matrix is far from 0 and from 1, then a lot of good things happen. I'll not go into the details. We have even sharp estimates about the probability of this thing related just to the Christoffel function of the original measure, so the polynomials. And this was used by two of my collaborators for the uniform distributed mass on the cloud, quite successfully. But we would like to go beyond, and we, of course, use results in several variables. Some of them are due to Crow and Lubinsky, analogs of what I mentioned here in 1D. And let me just jump to the main results, upper and lower bounds. What is interesting here, a new function which was not studied in the orthogonal polynomial community is this cosine function. So it's a very standard quotient of the polarized Christoffel function by its values on the diagonal. And this plays a major role in all estimates I wanted to stress. And in the end, we have the major theorem in 2D using complex variables gives you upper and lower bounds, how far you have to go with the discretization and the degree to have a good detection of outliers from the cloud. And everything depends on the green function of the cloud. Here. What is interesting here is the square, and I take 1 minute to mention. We can consider the square in 2 real variables, or we can deal with the square with 1 complex variable, or we can embed the square into C2 and deal with 2 complex variables. Which is better? Well, you can see here, this is the real variables. This is the one in C2, and this is the complex variables. And this will give a much more accurate, although there are some distances here, than the real ones. So conclusion, complex variables are superior, which we know already. And finally, what happens if the supports are on algebraic varieties? How we detect them? We can work not necessarily on the Euclidean space, but we can work, let's say, on the torus. We can work on a sphere, and there are good reasons to do this. And how we detect outliers and the level sets on such supports. I'll give you only pictures. This is real data. The orientation of a little fly related to the sun. This fly has an orientation, and what you see here are the level sets of the Christoffel function. And it shows how accurate they are compared to the orientation of this. And why I mentioned, because we have 2 angles here, and the 2 angles, like in mechanics, like in classical mechanics, they live on the torus. So here, the basis is not Euclidean, but rather the torus. And again, the Christoffel function turns out to be very accurate to the real data. If we look at double stars in the sky, again, this will detect, for instance, the Milky Way. These are the level sets of the Christoffel function, and you see the Milky Way in the distribution of double stars on the sphere now, because we treat the sky, just the projection on the sphere. So we live on another algebraic variety. To the torus, these are some DNA measurements. I'll not go into this, just to show you that this tool is very relevant for real applications. And let me finish by giving the affiliations of my collaborators. So this was work done over about 10 years. And only recently, we discovered that we are doing, in the fact, the same things. We all are using the Christoffel Darboux kernel from different sides. So these are my collaborators, and here are some references. You can see one of them is rather old, and the other are very new. If you want to have a bedtime story, very entertaining, about the Christoffel function, read this 164 pages article of Paul Nevai about his friend Geza Freud. Everything is about Christoffel functions, and it's very well written. It gives you the whole history, and it's extremely entertaining. Bedtime story. And then, as I mentioned, very recently, Barry Simon entered into this and uses this tool to spectral analysis. And the major result, I think the culmination of a century of work, is this Totic article. So I gave you just an overview. As you see, this old idea of comparing point masses to energy in some norm of a polynomial is very fruitful and can give really new interpretations of phenomena which are of interest of not only of mathematicians, other scientists today. Thank you very much.
So, thank you very much. Time for questions and remarks. We have time.
Too much.
So I have one question.
Please.
When you recovered the shape, the first application, do you have any statements about the rate of convergence in the interior?
Yes, precise, yeah.
I would like to see those.
Yes, well, it's in this Advances in Math paper. Yes, we do. Widom had them for the Hardy space, and what we are doing here is the analog for the Bergman space. So they are very classical. 1960, Harold Widom did them for a collection of islands, and this is the Bergman space situation. Precise estimates, yes.
I have a question to your application on the blackboard.
Yes.
The first, this is not seen completely. So you have there.
Oh, maybe I'll leave this. Yeah, just 1 second.
Yes, you have there this uniqueness result. This is the first application.
Yes.
And what you get are, in the end, Hankel operators. So
yeah, this is the Hankel matrix.
Yes, this is also an infinite Hankel matrix. And so does this result relate to boundedness of this Hankel operator, or how do I have to understand this limit in the end?
No, it's more complicated than that. Indeed, the lowest eigenvalue, when we truncate the infinite Hankel matrix and we look at the lowest eigenvalue, this is related to the Christoffel function, but on the line. What I emphasize here is a point like I, outside the real line. And this has to do, we take the multiplier by the variable in this inner product, is a symmetric operator, possibly unbounded. And this will tell you the defect numbers, whether this is essentially self-adjoint or not. And that was the discovery of Marcel Ries. It's an essential self-adjointness criterion. That's the symmetric multiplier by the variable has only one self-adjoint extension in this situation, and only in this situation. And then what Nevanlina did, he parameterized, they are all self-adjoint extensions are parameterized by the Weil circle, what is called. And what Nevanlina did, found exactly the parameterization in a constructive way using continued fraction expansions. So there is a whole history here about the meaning of this. This is the discrete analog of what Hermann Weil did for the Sturm-Liouville problem with a moving boundary much earlier. And he discovered that there is a limiting circle. And the radius of this Weil disk, of Weil circle, is exactly this function, up to a constant or something. So there is an interpretation, a spectral interpretation, but not immediately related to the eigenvalues of the Hankel matrix.
I have one question. Perhaps you can say something about whether these limits, you can give more precise asymptotics for these limits.
Oh, yeah. It's a big... So if we work with measures which are called regular measures, there is such a very standard concept. That means you have a Bechstein-Markov inequality for them. Then outside the support of the convex hull of the measure, this function will converge to the exponential of the green function with a pole at infinity of the respective distribution. So, and this is a very standard tool in approximation theory. It's well known. And we used it in one of these applications. When you have a green function, automatically you relate it to this.
But usually I think that the singular part of the continuous may give more problems than you.
Of course. And there is a puzzle, and this attracts a lot of attention. Barry Simon has, I think, 5-6 articles about, the title is, the singular continuous spectrum of a Schrödinger operator is generic. But nobody saw a singular continuous spectrum of a Schrödinger operator. So it's like transcendental numbers. We know they exist, but we don't touch them.
Thank you.
So if there are no further questions, then let's thank Mihai again.